Okay, so in the last class we have defined the isomorphism between two vector space, and we have seen that the definition is if two vectors finite dimensional vector space are isomorphic, if there is a bijective mapping, bijective linear transformation from one vector space to another vector space. So, and we have stated this theorem in the last class that if V is a finite dimensional vector space over the field F, it could be real field also. F is any general field, it could be over R also. Then we can show that V is isomorphic with f to the power n. Okay. So, this we are going to prove now. So, how to prove this? So, suppose V is dimensional n, so we consider a ordered basis of V. Be a ordered basis of V. Okay. So, ordered basis means we are not changing the position of this. So, alpha coming before alpha 1 coming before alpha 2 like this. So, there is a well ordering like this. So, why we take this? Because we know the coordinate, right, coordinate of a vector. Now, if we take a vector A, alpha belongs to V. Now, alpha will be written as linear combination of this alpha n, and we know this coordinate, this alpha, this a1, a2, an, these are called coordinate of this alpha with respect to this ordered basis. Now, this is unique, this is called we discussed this one in one of the class. This is called coordinate of alpha with respect to this ordered basis. Okay. So, we take a ordered basis, then we take the coordinate, and then since this is a ordered basis, so it will not change the position. So, that means coordinate will be the unique. We know this is unique, that is why you need to take the ordered basis. So, now we defined a mapping, and this is coming from basically f to the power n. So, that is our mapping, because this is a. So, now we define a mapping from u to v, u to f to the power n as. So, T alpha is going to basically this coordinate of this. So, we take a alpha, we write this alpha with respect to the linear combination of this ordered basis, and that coefficient will give us the coordinate, and we take that transformation from alpha to this field. So, this belongs to f to the power n. Okay. So, this is the, now we need to show that this is a mapping, because this is, since this is unique. So, this is a mapping. So, this is well defined mapping. So, we need to just show that this is a linear transformation, and also it is a bijective mapping. Okay. How to show this is a linear transformation? Suppose we take another beta from here. So, our ordered basis is alpha 1, alpha 2. So, alpha is basically summation of a I alpha I is equal to 1 to n. We take say another beta, this is summation of say b I alpha I is equal to 1 to n. Okay. So, that means now if we take a alpha plus b beta. So, this is nothing but we have to find the coordinate of this, then only we can get T of a alpha plus b beta, where it is going. So, a alpha plus b beta we can just write as summation of a I plus b b I alpha I. So, that means this is the question. So, that means this is nothing but a1 plus b b1 first coordinate, then a2 plus b b2 like this. Okay. So, a n plus b b n like this. So, this is the coordinate of this. So, that means T of this is going to this. Okay. Now, this is basically written as A of T alpha plus B of T beta, because this T alpha is nothing but this and T beta is basically B1 B2 Bn. So, this is linear. So, T is linear. So, that means T is a linear mapping. Okay. Now, we need to show that this is a bijective mapping, then only we can say these two are isomorphic. So, how to show this is bijective? So, for bijective, first we have to show the 1 to 1. For 1 to 1, just we can just have kernel of this. Suppose we take a T alpha is equal to 0 vector. So, this is 0 0 0. Okay. So, now alpha will be written as what? Alpha will be written as 0 into alpha 1 plus 0 into alpha 2, like this, 0 into alpha n. So, this is basically 0 of u. So, the kernel of T is nothing but only 0 of u. So, this implies T is 1 to 1, and also similarly we can show T is onto by the rank nullity theorem, because this rank nullity theorem is telling us what? Rank nullity theorem is telling us dimension of kernel of T plus dimension of range of T is basically dimension of u. Now, dimension of u is, so this is 0. So, 0 plus dimension of range of T is basically this is n. So, dimension of range of T is n. So, that is basically f of n covering. So, this is basically onto also. So, this is a 1 to 1 mapping. So, that means this f u and f to the power n is isomorphic. So, u is isomorphic with f to the power n, sorry, f to the power n. Okay. If u has a dimension n and f is the underlying field. Okay. So, this is the isomorphism. Now, we define the linear set of linear space, basically the space, this is space u comma v. We consider set of all linear transformation from two vector space u v. So, over the same field. Okay. Now, let u v is the u v are two vector space, u and v be two vector space over the same field, and if we consider two linear transformation T of T and S, say. Okay. These are two linear mappings, say. Now, we define a plus mapping. How to define? S T plus S, T plus S is also a mapping from u to v. The definition of T plus S is basically we take alpha on this. So, this is basically T alpha plus T beta. This is the definition. This is how we define plus operation. This is the plus on the this is one operation on the linear transformation, and we will see this will form a vector space basically over the same field f. So, that we will see slowly. So, now first of all we need to show this is a linear transformation, this T plus S. So, how to show that? T and S both are linear transformation from u to v. So, how to show T plus S is also linear transformation? So, for that we need to show. So, suppose T plus S is W. So, we need to show W of A alpha plus B beta is basically A W alpha plus B W beta. So, this is nothing but what? This is nothing but T plus S. So, T of A alpha B beta plus, sorry, this is basically W is T plus S. So, this is S, sorry, this is wrong, this is S of alpha. Yeah, we are having alpha. So, we are first applying T alpha plus S alpha. So, this will be first we are applying T alpha, T of that plus S of that. Okay. So, now we know T is a linear transformation. So, this will be written as A T alpha plus B T beta, and we know S is also a linear transformation. So, this will be similarly, this will be written as A S alpha plus B S beta. Now, if we simplify this, and these are all operation over the vector space V, and this is commutative and associative. So, we can just write this as A of T alpha plus S alpha plus B of T alpha plus T beta plus S beta. So, this is nothing but A of W alpha plus B of W beta, but W is this. So, this implies this is a linear transformation, linear mapping. Okay. So, this plus we defined on the two transformation. So, that plus is also a linear term. Now, we define the scalar multiplication of this linear transformation, and we will see that is also a linear transformation. So, we take a linear transformation from U to V. Now, we define alpha t, sorry, A t scalar, A t, where A is coming from the scalar. Okay. So, how to define this? This is some sort of a scalar multiplication, but not we are defining this scalar multiplication, but for simplicity we are just writing A t. So, A t of alpha is basically A of T alpha. This is the definition. This is how we define A t. So, that means A t we have to show this A t is also this is basically referred as A t, which is basically say some W we use, some W 1 or something. Anyway, this is a mapping. This is a mapping from U to V, because this is a V vector and this is a scalar. Now, this scalar multiplication on the vector V. So, this will give you a vector in V. So, this is a mapping. So, A t is a mapping from U to V. Now, only thing we need to show that this is a linear mapping. So, for that what we need to take? Again we need to take some A t of some C 1 alpha plus C 2 beta, and this we have to write C 1 A t alpha plus C 2 A t beta. Okay. So, how to write this? So, this is nothing but by definition this is a element in U. So, this is basically A of T of this C 1 alpha plus C 2 beta. This is the multiplication in the scalar multiplication in V. So, now T is linear. So, this is basically C 1 T alpha plus C 2 T beta. Now, this we can write here A C 1 T alpha plus A C 2 T beta. Okay. Now, this is from the associative property of the this is the scalar multiplication property of the vector space. We know that it distribute. So, now this is again we can write, because this is coming from F, this is also field. So, this is commutative under that field multiplication. So, this will be written as C1 A T alpha plus C2 A T beta. So, this is nothing but C1 A T alpha, A T is the operation, A T is the transformation, plus C2 A T beta. So, this implies A T is a linear transformation, A T is a linear mapping, is linear. So, if T is linear, then the way we defined A T as this is also linear. Okay. So, now it is time to see whether this set of all linear transformation will form a vector space over the field, same field F under these two operations, like that plus operation, plus of two linear transformation and the scalar multiplication. So, that is the space called LUV. So, LUV is the set of all linear mapping from U to V, from two vector space U to V over the field, same field F, and then this UV is also a vector space over the same field F under the two operation plus means that T plus S. This, if we take two linear transformation, just now we have seen how we define plus. So, plus of alpha is basically this is itself is linear transformation, we have seen T alpha plus S alpha. This is the way how we define the plus. Under plus and that dot means we have seen that AT, this AT is a linear transformation again, just now we have seen. So, AT of alpha is basically A of T alpha. So, this is the our definition of these two operations. This is a vector space under plus and dot. So, for that we need to show certain properties of the vector space. So, for vector space we have to show this will form a abelian group with this, okay, and also this scalar will be distributed over these are the properties. So, one can easily verify that. So, this space is called a space LV. So, later on we will see the dimension of this space when we bring the matrix into the linear transformation, how we can visualize a linear transformation as a matrix. So, just we will introduce that now. Okay, so, now it is time to see the relationship between the linear transformation and a matrix. Okay, so, this is called matrix representation of a linear transformation of a linear mapping. Okay. Now, suppose we have a linear transformation, let T be a linear transformation between two finite dimensional vector space U and V over the same field F. So, we have a two vector space U and V over the same field F and they are finite dimensional, and suppose dimension of U is say n. So, dimension of U is n and dimension of V is say m. Okay. So, now if they are m n, so then there has to be a basis. So, suppose B1 is the ordered basis of U. So, it is n dimensional, let B1 be an ordered basis, be an ordered basis of u, and we take B 2 which is basically beta 1, beta 2, beta m be an ordered basis of V. So, we took two bases. Ordered basis means we want to have the coordinate. To have the coordinate which is unique, we need to have the ordered basis, otherwise the coordinate position will change if these are not in order. So, we take two bases, one is from u, another one is from V. So, alphas are from u and betas are from V. Okay. So, now we have a linear transformation from T to u to V. So, this will map these alphas to betas. So, let us write that. So, T of alpha 1 will map to will be a vector in V. So, vector in V will be written as some linear combination of the basis, ordered basis. So, suppose that is basically a 1 1 beta 1 plus a 2 1 beta 2 plus how many elements? There are m elements. So, a m 1 beta m. It has to be written as a linear combination of the basis of this, because this T of alpha 1 is a element in V. Similarly, T of alpha 2 we can write as a 2 1 beta 1 sorry a 1 2 and plus a 2 2 beta 2 plus dot 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 a m 2 beta m, this way. Okay. So, this way we continue. T of alpha I or alpha j will be written as a 1 j beta 1 plus a 2 j beta 2 plus a m j beta m dot dot dot. We have alpha 1 alpha 2 alpha n. Alpha n is equal to a 1 n beta 1 plus a 2 n beta 2 plus a m n beta m. So, these are the basically the coordinate of this is a 1 1 a 2 1, this is the coordinate of alpha 1. So, what is the coordinate of this alpha j? Coordinate of alpha j is basically a 1 j a 2 j dot 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 a m j. So, this is basically coordinate of T of alpha j. Okay. Now, we write this in a matrix form. The first column of that matrix is the coordinate of this like this. So, this we have to remember. So, this is the way we are writing. So, now we will write this as a matrix form. So, this is the coordinate. Now, we take any element alpha from here. So, we will just yeah, we can remember this. So, now we take an arbitrary element from U, and this will be written as x 1 alpha 1 plus x 2 alpha 2 plus x n alpha n. Okay. So, now we want to apply T of this alpha. T of this alpha is basically T of this. Now, T is a linear mapping. So, x 1 T of alpha 1 plus x 2 T of alpha 2 plus x n T of alpha n. Okay. Now, alpha 1 we know alpha 1 is basically, if we write that earlier form, it is basically a 1 1 beta 1 plus, we want to write in terms of beta si, because this has to be written as a linear combination of betas, because betas are the bases in V. So, a 2 1 beta 2 dot 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 a m 1 beta n plus x 2 of like this a 1 2 beta 1 plus a 2 2 beta 2 plus a m 2 beta m. So, like this we continue plus x n of a 1 n beta 1 plus a 2 n beta 2 dot 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 a m n beta n. So, this if we simplify this will be written as some form of y 1 beta 1 plus y 2 beta 2 plus dot 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 y m beta m. So, this is the way we write this. So, now this y I are nothing but coming from the multiplying the matrix. So, this is basically y are coming from, if we put the matrix over here, this A matrix by the coordinate of alpha 1, coordinate of alpha 1 is basically 2 1 a 3 1 dot 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 a m 1. So, a 2 2 a 3 2 a m 2. So, last is alpha n. So, a 1 n, a 2 n, a 3 n dot 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 a m n. So, this is a matrix A matrix. So, this is nothing but we take the first column as a coordinate of T alpha 1, T alpha 2, T alpha n. Okay. Now, if we multiply this with that x 1, x 2, x n, which is basically the coordinate of that alpha, and that will give us this beta, this y. So, this is basically y 1, y 2, y m. So, this is the matrix A matrix. So, y is nothing but a x, where x is the coordinate x 1, x 2, x n, it is the coordinate of alpha, coordinate of alpha with respect to that basis beta 1, then the y is basically y 1, y 2, y m, which is basically the coordinate of T alpha with respect to beta 2. So, that means, if we know this matrix, we can get the transformation. If we know this matrix, then any vector can give us this coordinate. So, if we multiply this, it will give us the coordinate of the vector in V. Okay. So, that we will take an example, a quick example, and this matrix is A matrix. We will take a quick example on this. Okay, suppose we have a linear transformation from R 3 to R 2. We define T of x 1, x 2, x 3 as 3 x 1 minus 2 x 2 plus x 3, then x 1 minus 3 x 2 minus 2 x 3. Okay. Now, we want to get a matrix on this, we want to get a corresponding matrix for this linear transformation. Then, if we know the matrix, then the transformation is given to us. Okay. So, for that we take a basis from R 3, say we take the standard basis 1 0 0, 0 1 0, 0 0 1. This is our B 1. We take the standard basis of R 3, and then we take the standard basis of R 2 also 1 0 0 1. Okay. Now, to form that matrix, this is our alpha 1, alpha 2, alpha 3, and this is our beta 1, beta 2. Now, to get that where alpha 1 is going, so you have to take alpha t of 1 0 0, alpha 1, t of alpha 1 is basically, if you calculate, it is basically 3 comma 1, just if you put the value over here, and this we are to write as beta 1, beta 2. So, this is basically 3 of 1 0, plus 1 of 0 1. So, basically 3 1 is the coordinate for this T of this in terms of this basis. So, this 3 1 will be the first column of the matrix. Now, similarly, if we calculate this, this is basically minus 2 comma 3. So, this is basically minus 2 1 0 minus 3 0 1. So, the matrix is first column is 3 1. So, the second column will be minus 2 minus 3 and the third column will coming from T of alpha 3. So, this is basically if we do the calculation 1 comma minus 2 1 comma 0 minus of. So, that means 1 comma minus 2 is the coordinate for this. So, this is basically. So, this is the matrix corresponding to that linear transformation. So, if you know the matrix, then how we will get the transformation? If you take any vector, alpha which is basically x 1 x 2 x 3. So, which is written as x 1 into this under this basis. So, x 2 into 0 0 1 plus x 3 into 0 0 1 0, this is 0 0 1. So, that means this x 1 x 2 x 3 is the coordinate of this alpha with respect to this basis. Now, if you multiply this with the matrix x 1 x 2 x 3. So, this will give us. So, this is 2 by 3, this is 3 by 1. So, this will give us 2 by 1. So, this is y 1 y 2. So, basically T of alpha is basically y 1 plus y 2 of 0 1, because this we get the coordinate by multiplying this with this, and this is our T of alpha. Anyway, we will talk about more details on this. Thank you.